In the last video, we saw that the derivative of the exponential function b to the x was b to the x times the natural log of b. All right, remember in an exponential function, the base is a variable and the exponent is a variable. Okay, so let's take a look at an example. All right, if we take the derivative with respect to x of 2 raised to the power of x, so we have the constant base of 2 and the variable exponent of x, so this is an exponential function. All right, the derivative will be 2 to the x times the natural log of 2. Now notice that 2, okay, of course, is greater than 1. This implies that the natural log of 2 is positive. So exponential functions themselves, 2 to the x, are always positive. And since this natural log of 2 is positive, we have a positive exponential function times a positive logarithm. So the result is going to be positive. So this is greater than 0. That means, and remember this is a derivative, so this tells us the slope of the tangent lines, all right, for the exponential function 2 to the x. So all the tangent lines will have a positive slope. If we look at the graph of 2 to the x, which we have here, any place along this graph where we have, if we look at the tangent line will be sloped in the positive direction. Let's take a look at another example. Let's suppose that f of x is 1/3 to the x power, and let's look at f prime. Well, f prime, again, notice the constant base of 1/3 and the exponent is a variable, x. This is an exponential function. So its derivative is going to be, all right, the exponential function itself, 1/3 to the x, times the natural log of the base. And now in this case, since 0, the base is between 0 and 1, 1/3 is between 0 and 1, this implies that the natural log of 1/3 is negative. So for this derivative, we have a positive exponential function times a negative logarithm. So a positive times a negative number means we get a negative number. This result is less than 0. So in this case, remember the derivative tells me the slopes of tangent lines. So for the graph of this function, the slopes of the tangent lines are always negative. And if we look at the graph, all right, if we take a look at any of the tangent lines, okay, notice they'll have a negative slope. All right, way over here, they'll have a slope very close to 0, but it will still be slightly negative. Right? There's a very special exponential function, e to the x, and here's what makes it special. If we take the derivative of this function, again, remember the base is e, which is roughly 2.71828. Remember that number is irrational, so this keeps on going. All right, and then since the base is constant and the exponent is a variable, this is an exponential function, so its derivative is going to be that exponential function times the natural log of base e. Again, since e is greater than 0, well, we could actually go farther than that. Notice that the natural log of e we've seen earlier is 1. So this is really just e to the x. All right. So here's the thing. The derivative with respect, this is what makes this function so very special. The derivative of e to the x with respect to x is e to the x. E to the x is its own derivative. And that's what makes it so important in examples. Of course, this is a positive number. All right. So the derivative is greater than 0. Slopes of tangents will always be positive. And here's the graph of e to the x. All right, now let's take a look at some a little more complicated examples. Suppose that we have y is equal to, notice the constant base, but in this case, the exponent is not just x, it's some expression involving x. Well, we could use logarithmic differentiation to take this, to figure out what dy dx is. So let's take the natural log of each side. Notice that on the right side, the g of x is the exponent, and because of our log properties, this exponent g of x can come out as a multiplier on the base of times the natural log of the base b. And so now if I take the derivative of each side with respect to x, notice what we get here. Well, on the left-hand side, remember y, we think of y as a function of x, so the natural log of y is a composite function. We'll have to use the chain rule, take the derivative of the outside function. That's 1 over x, but we evaluate it at the inside function y times the derivative of the inside function times y prime. On the other side, we can take out the natural log of b because it's a constant factor. And I'm just left with the derivative with respect to x of g of x. And that would be just g prime of x. So y prime is going to be y times the natural log of b times g prime of x. And remember, y was b to the g of x, so this would be dy dx, which is y prime, is equal to b to the g of x times the natural log of b times g prime of x. Let's take a look at an example here. All right, so let's suppose, and these, you may find it easier always just to go back to logarithmic differentiation, but you could use that formula. In this case, the g of x would be x squared and b would be 5. And so if we took the derivative of this, remember, let me write it up above here, the derivative with respect to x of b to the g of x was b to the g of x times the natural log of b times g prime of x. So this would be 5 to the x squared, right, times the natural log of 5 times the derivative of x squared, which is 2x. And we may want to rewrite that in a different order. Let's take a look at another example. Okay? In this case, the derivative of e to the g of x. All right, well, using that same formula, let me write it up above here, that the derivative with respect to x of b to the g of x was b to the g of x times the natural log of b times g prime of x. Well, this would be e to the g of x times the natural log of e, natural log of base, times g prime of x. And of course, this natural log of e is 1, so this becomes just g prime of x times e to the g of x. So the derivative with respect to x of e to the g of x is simply g prime of x, the derivative of the exponent times e to the g of x times the original exponential function. So let's take a look at this derivative. The derivative with respect to x, remember this is because of the special properties of the base, our e, that the natural log is 1, is going to be the derivative of the exponent cosine of x times the exponential function itself. Another example, if f of x is e raised to the x squared plus 3x, f prime of x will be equal to the derivative of the exponent, 2x plus 3 times e to the x squared plus 3x. The derivative of the exponent times the original exponential function. Notice that lots of students would tend to leave out these parentheses, but of course, if that's the case, then you're just multiplying this exponential function by 3 rather than the entire derivative of that exponent. And this is how you differentiate exponential functions. There is maybe a summary sheet that the derivative, if we have the special base e, the derivative of e to the x is e to the x. It's its own derivative. The derivative of e to the g of x, we could think of this as the chain rule formula, is the derivative of the exponent times the original function e to the g of x. When the base is not e, we just have to remember to multiply by this natural log of the base. So the formulas otherwise are the same. The derivative of b to the x is b to the x times the natural log of b. The derivative of b to the g of x is g prime of x times b to the g of x, but then times that natural log of b. So remember, multiply by the natural log of the base. When, well, you can think of it in any case, but in this case where we have e to the, if the base is e, the natural log is 1, so we don't really see that. We've been multiplying by it. Okay, this is how you take the derivatives of exponential functions.